do not have with Laplace. And duality's probably, in my opinion, the most important property. Everything else is more or less the same. For instance, convolution, if you convolve two functions in the time domain, if it's Laplace, it's what? Just multiplying the two functions, right? The Laplace domain, correct? With Fourier transforms, it's the same thing. I'll mention these two just for completion. And then, but I do want to make sure I emphasize the importance of duality. And I'm going to do the triangle function. I'm going to show you how you get it using the property. And I'm going to actually show you a few things you can do with that pulse functions that are really nice. That will help you do a lot of Fourier transforms. Okay. So first, if we have a function go x of t goes to, oh boy, still a little bit, goes to x of omega. We assume we know that relationship. Then, oh, this is going to be fun. I really don't want to do this. But then we can say that if we have something where we have x of t convolved, this is convolution with h of t in the time domain, that's simply going to be x of omega. There's no other paper towel? Sorry, this stuff's still wet. I'll try over here. Maybe I can find a draft part of the book. But really what I'm saying is it's going to be x of omega times h of omega. Does everybody understand that, class? So it's just multiplication. I can prove that. But you remember with Laplace you could do that? How many do? All right. Well, it's the same field. Thank you. It's the same deal here. Now, that's real important because now, I mean, we can make use of this just the way we did with Laplace. Understand? There's nothing really different about that. Convolution, time, multiplication, frequency by the two functions, and then you can do partial fraction expansion. I'm going to make a comment here. Now, when I give you problems, either Laplace or Fourier problems to do, if the functions are only valid or only have values that aren't 0 for t greater than 0, then I'm going to make a suggestion. Use Laplace transforms and then at the end let s be equal to j omega. So for this, generally speaking, when we had, thank you, just leave them right there. Yeah, I'll probably be grabbing away. But then we can say that it's simply just let s be j omega. If the functions are non-zero only for t at 0 or greater than 0. Are you with me, class? It's the easiest way, in my opinion. Now, there is one exception, the u of t function, right? Because the one thing about Fourier transforms is that they have to have a finite integral value for the integral of the function from over the domain. It has to be less than infinity to do a Fourier transform. Do you understand, class? In order to do a legitimate Fourier transform. And I'm not going to spend a lot of time on this. The ones that are a little different, I'm going to list right here. All right? So everybody will know. The first is really u of t. U of t for Laplace is just 1 over s, right? But with Fourier, because this thing integrated from 0 to infinity is not 0. You follow? I mean, it's not finite. It's infinite. Do you agree? Mm-hmm. Because of that, this has that delta function. This will go as what?
1 over
it's going to be
j
1
omega.
over j omega. That is the 1 over s term. But then it's going to have the plus pi times delta of omega, and that's due to the DC component of energy or power, or particularly energy at DC. Do you understand that, class? And we proved that. We can do it with duality. This is one. Now, another function that you'll see over and over again, we use the pulse function. I mentioned that last time. You're going to see the pulse function of t, which in the book they use rect of t over tau. And everybody knows, I hope, that it looks like this from minus tau over 2 to tau over 2. It has a value of 1. This is the pulse function of tau, or rect of tau. Right? Well, that one's got values for t less than 0 that are not 0. Right? So you can't just go with a Laplace on that. Do you follow me, class? You have to do a Fourier on this one. And when you do the Fourier transform of this one, then you get the tau times the sinc of omega tau over 2. And the sinc, of course, is a very important function because really this is equal to tau times the sine of omega tau over 2 divided by omega tau over 2. It's the sine x over x thing. And that's really what the sinc function is. I'm putting it there for everybody's, just to make sure we underscore that fact. Understand, class? Now, the next function is the one I didn't prove. It's the triangle function. I like this for the triangle function of t. In the book, he won't use that, unfortunately. At least I didn't see it. What he does is state the mathematical definition of this. He says this is really equal to simply, this is equal to 1 minus 2 times magnitude of t over tau times the pulse function of tau of t. Now what this is just a straight line. What's the value of this function at t equals 0? Well, t equals 0, isn't it 1? What about at minus t over 2? Well, if tau over 2. If it's tau over 2 times 2, it's just tau divided by tau is 1. 1 minus 1 is 0. Do you all see that? And what this function looks like here, or this triangle function, is this. I'll get out of your way in a second. It looks like that. They have this in the book, though. Just write down the triangle there. All right? Are you with me? Now let me show you something. We could get this, get the Fourier of this. I'm going to put it down, and I'm going to prove it. This is going to be tau over 2 times the sinc squared of omega tau over 4. When you look in your books, do they have this one? Can you see this functional form and this as the transform, Fourier transform? I know some of you have your books there. Take a look. I see 1, 2. You good, Josh? It should be this, is what you'll see. It will be 1 minus 2 magnitude of t over tau times the pulse function, but they'll have a rect instead of a pulse. You don't see it? All right, well, guys, if you don't see it, write it in there. This is really important. I know it's there somewhere. The problem is, it may not be in the tables. You may have done that as a problem. This is a real important one. Now, I'm going to show you how you get it, all right? Work with me on this. I'm going to say my x of t is going to be equal to the triangle function of tau of t. All right? I'm looking for that transform. I don't know what it is. I'll call that x over omega. Now, when I take a derivative of x of t with respect to t, what do I get? Think about it. If this is minus tau over 2, and this is tau over 2, and this is my pulse function of t, triangle function. Triangle function of t. Then when I take a derivative, it looks like this, right? Just take a look at this. Now I'm going to show you the derivative of this. This is equal to my x of t. Now I'm going to show you dx dt here. Take a look at this. At minus tau over 2, which is tau over 2. What do you see as the derivative? Just take a look. For t from minus infinity to minus t over tau over 2, isn't it 0? What happens at tau over 2, minus tau over 2? It goes from 0 to
2 over tau.
Then it's going to be the rise is 1 over the run would be tau over 2, or it'd be 2 over tau. Do you agree? Mm-hmm. So the height jumps up to 2 over tau. How long does it stay there? Say it again. It's going to stay there till 0, right? Now what happens from 0 to tau over 2?
Negative 2 over tau.
Same magnitude, only
Opposite sign.
it's opposite, right? Now it goes this way. It's minus 2 over tau. Do you agree with that? Do you all agree that those two could be represented as pulse functions of a certain width with a time offset, right? I'm going to do it to be, I want to make sure you're real clear on this. So let me do it this corner of the board to show you what I'm talking about. Now we agree if, just work with me, this x of t is not this x of t. if you have x of t equal to p tau of t, I'm not going to use the rect. We know that goes tau times the sinc of omega tau over 2. And everybody agrees with that, correct?
Yeah.
Right? I wrote it up there. You got to know this. Are you agree, class? Now, what I'm going to do, what happens if I have x of t minus, say, alpha? That's p tau of t minus alpha, right? What is that actually doing? It's shifting what? The center point of the pulse function, correct, class? Now I can start it at 0 if I want. If I make that be p of t minus what? Tau over 2. And that's shifted exactly tau over 2. And now the center of it would be a tau over 2, and it would span would be tau. So it start at 0, stop at tau. Do you agree with that, class? Well, what's the transform of this? What property am I using? It would be x of tau, this, right? But then I'd have to multiply e by times e to the minus j omega alpha, right? Whatever the time shift is, agree?
Yes.
So now I'd say this would be e to the minus j omega alpha times that, times tau, times sinc of omega tau over 2. That's just repeating this here. Sorry, I worked myself into a corner. You all see that there, class? All right, now I'm going to go one. The next step is making alpha be tau over 2. Working with me? So now we can draw this one. So now when I have p tau of t minus tau over 2, that becomes e to the minus j omega tau over 2, right? Times tau times the sinc of omega tau over 2. Do you all agree with that? Agreed? What does this function look like? It's centered where this is 0, right? Correct? Where the argument here is 0. Where is that? Where t equals tau over 2. You would put t minus tau over 2 is 0, or t is tau over 2, right? That's where it's centered. What's the span? Tau, right? So you would go this way by tau over 2, this way by tau over 2, and it looks like this. You agree with that? This would be this function, correct? And this would be its transform. Do you all agree with me? How many see this right here? Y'all see what I'm up to right now? Look what I got over there. Yeah. Go ahead, Josh. I didn't scale it yet. I just put,
Okay.
I'm about
That's
to.
what I was going to ask.
I'm about
All
to.
right.
Since he brought it up. Now I'm going to multiply this by this. Got me, class? And you'll notice the span of this also is what? This is 0 right here. Now the span of these, either one of these two pulse functions is not tau, but it's tau over 2, isn't it, class? You all see that? How many see it? I'm going to go ahead and I'm going to do it. Catch up with me. First, agree with me here. Right? Now that is the width, correct? So if I do this, follow me, make this tau over 2, this, the center, would be tau over 4, do you agree? This would be tau over 2, right? And then this would be tau over 2, divided by 2, or tau over 4. I hope you all appreciate what I'm trying to do, and this would be tau over 4 as well. And then this is what I'm doing. This would look like, this would be now tau over 4, and this would be tau over 2. The span now is tau over 2. That's the width. The center point is tau over 4. Do you all see this, class? Give me a show of hands if you do. Come on, what don't you see? Can you read it? Am I writing out there?
They're talking to me. I'm just trying to picture it.
No, not you, Megan. I'm talking. Are you all seeing? Can you not see it or not?
I can see on the front.
Only thing I've done is replace the width by tau over 2, right? And then the center point can't be tau over 2. It's got to be tau over 4. It's got to be half the width. That's the reason to put it, right? Now, what is that right there? It's almost that, right? Except it's got to have a minus 2 tau, the 2 divided by tau in front of it. Do you agree? And I'm going to do this, but if I put a minus 2 over tau here, don't I have to put a minus tau over 2, 2 over tau here as well? You all see that, class? Give me a show of hands if you do. So I can make this fit this part, right? But now where's this one centered?
Negative tau over 4.
Minus tau over 4, right? Can't we make that fit that by doing only one thing? By making that a plus, correct? Right? And if we make that a plus, we make this a plus as well, don't we, class? Right? So, that said, what I'm going to do is first describe these two mathematically in terms of a pulse, then do the transform of this, right? Now listen, once I have the transform of that, what is the relationship between this and this? Between this function and this function? This is the derivative of that function, right? So I know if this goes to j, or to really x of omega, then dx dt would go to j omega times x of omega, wouldn't it, class? You agree with me there? That's a simple property. So I'm almost done. Keep watching this, you'll see. Let me go ahead and use this part of the board. It's dry by now, I hope. The reason I'm spending a little time on this particular one is so important to know. So now I'm going to describe this mathematically. Work with me. For the first part, from minus tau over 2 to 0, can't we say my dx dt is really equal to 2 over tau would be the height, wouldn't it? And there would be a pulse function, right, of with what? Tau over 2, t, go ahead. Where's it centered? Plus tau over 4, correct, class? That's this part right here. Make sure you know how to write that. You already with me? That's a pulse with tau over 2, centered at minus tau over 4, correct? And it has a height of 2 over tau, correct? Now we're going to take that, then we have to take care of the second part, which would be minus 2 over tau, correct? Times what? Just tell me.
Pulse.
Pulse, go ahead. What with?
Tau over 2.
Tau over 2, centered at? Agreed? Are you with me? It's straightforward. You have to be able to see this logically. It makes perfect sense if you think about what I'm doing. Take the derivative, define the derivative in terms of pulse functions that are now time shifted. Now, let's take the transform of both of these. All right, so now I'm going to get the transform of dx dt. What happens when you do it? Just do it here. You all agree that that 2 over tau just comes down? You agree with me?
Yeah.
So I'm going to do it. I'm going to put 2 over tau here. Now, I know they appear both there and there, right? Now, what's the transform of the pulse function offset by tau over 4? It's always the width, or tau over 2 in this case, right? So it'd be tau over 2, right? Then it's going to be times the sync, right? But it's what? Omega times tau, which is the width, which in this case is tau over 2, divided by 2, or now it's tau over 4. Do you agree with me? Please look at this. Make sure you agree with the logic. Can you read that, Josh, or not? From there? Can you see it in the back? I see people screaming. I don't know if it's me or... So what about the next part? What happens? Remember, I factored out that 2 over tau. What's the next part? What's the width of that one? Tau over 2, correct? So that's the first thing that comes out there. So now it's tau over 2 times the sync of what? Oh, wait, I did one thing. I didn't do one thing. So I forgot that, right?
Yeah.
So I'll put it in right now. That would be e to the j omega tau over 4. Remember, that's a plus. Then the next part is what? Plus tau over 2, right? Times the sync, right? The sync function, right? Then it's going to be omega times the width, which is tau over 2, divided by 2, or tau over 4, but then times what? Say it.
Minus j.
Right, thank you. E to the minus j omega, minus j omega, and then it's tau over 4. Okay? Not quite there yet, but you can see I can factor out First, you see the 2 over tau and tau over 2 stuff just cancels, doesn't it, class?
Yeah.
Can you all see that? Y'all follow me? Maybe you are.
So the second part be minus tau.
Yeah, you're absolutely right. That was my bad. This is minus. Whole class here, better cases. Okay? You got me on that one, right? Now, if you all see the tau over 2's cancel, this tau over 2 times 2 over tau cancels, right? It's 1. Show of hands here. How many see that? Make sure everybody does. So I'm going to, if you don't mind, are you okay with me erasing this? All right. So I'm going to erase that and that and that to make my life easier. Now, in the next line, I'll write it. You all see I can factor out the sinc of omega tau over 4?
Yep.
Agree? So if I factor that out, what do I get? I get the sinc of omega tau over 4 here, and then it's times e to the j omega tau over 4, right? Minus e to the minus j omega tau over 4. I agree? Any clue what I might do next?
Got a sign.
Sure does look like a sign coming up, doesn't it? E to the minus j omega tau, or e to the plus j omega tau over 4, minus e to the minus j omega tau over 4 is really the sine of omega tau over 4 times 2j, isn't it? I'll put it down here. So this is going to be the sinc of omega tau over 4 times 2j times the sine of omega tau over 4. And that's this is the transform right here of the derivative of x with respect to t. Do you agree with that? Agree? This is the derivative, the transform of the derivative of x of t, correct, class? X of t was the triangle up here, right? But what do we know? If we knew this transform that we want, right? Then if we took the time derivative, effectively what happens over here? Wouldn't that just be j omega x of omega? Do you agree with that? Isn't that right? A time derivative just brings over a j omega in front of the actual Fourier transform. Do you remember that, class? Do you? Right. It's straightforward. So now what I can say is this, which is the transform of the derivative, is equal to j omega, really, let me make that a little better. That's equal to j omega times x of omega, right? That's the transform I want. Are you agreeing with me? Agree? Now what happens? When I divide this by j omega, right? Just take a look. I'm almost ready to go for a sinc. But what? If I put j omega, the j's cancel, right? Then I can take the 2 downstairs, right? Now I have omega over 2, but I need omega over 4. So I multiply top and bottom by a half. I'm going to do this in a second. But I'm going to find a way to make that appear downstairs so I can replace that sine of omega tau over 4 divided by omega tau over 4 by a sinc. Are you with me? And I'm going to do it. I'm going to do it right here. So you can see this. This is a really good, this kind of stuff, it shows you how to think about these transform things when you deal with them. When you get some weird functions, you always think about derivatives, integrations. Same way of getting that from something you know. So now I can say the actual x of omega I have is this. Now, will you all give me that I can get rid of that j here? Right?
Yeah.
And all right, I'll start there. So this is going to be equal to, it's actually omega times this. Omega times that is equal to the sinc of omega tau over 4. Then it's times 2. And then it's going to be times the sine of omega tau over 4, right? Agreed, class? Now, the next step is divide both sides by omega. When I do that, I get this. Then I can take the 2, divide top and bottom by 2, And now I got that, right? Then I have to divide top and bottom by 2 again. Do you agree with me? Right, and when I do that, I get 1/2 here, and that becomes a 4. And what's the last step before I got it to the 4 minus 8? Class? Top and bottom by tau, correct? Multiply top and bottom by tau, and I get a tau there, and that's the tau, right? And now, what do you see happening? The last step, very last step. What is this? Huh? That's a sink of omega tau over 4, and that's a sink of omega tau over 4, right? Or my x of omega then can be defined as simply tau over 2 times the sink squared of omega tau over 4. And that's the one you have to know for a, this is really, this is a triangle, this is the transform of the triangle function. Just remember that. It's squared here, it's got tau over 2 in front, not tau. But that's how you get it, using the property of a derivative. Yes, sir?
So initially you had, you said that the derivative of x of t is equal to j omega times x of omega.
I said x of t was the triangle function, right? And the triangle function had a transform we called x of omega, right? Then when we took a derivative of x of t, we get dx of t, we had 2 pulse functions, right? Those 2 pulse functions, I knew the transform of. And I knew that anytime you have, it's the most common property, right? Anytime you have dx dt, what do you really get over here? It's just j omega times x of omega. Whatever omega, if x of t goes to x of omega, then the derivative of x of t is just j omega x of omega.
Right.
That's how we get it. Right?
I hear what you're saying.
It's honestly, if you look at this, it makes perfect sense. There's no trickery in this one. It's straightforward. Just realize the power of using those properties. That little property here saves you a lot of integrations, a lot of problems with integration by parts. All right, that one I wanted to work for you, make sure you have that down. I'm trying to give you the properties that are most important. I got 1 or 2 more. Let me just do one thing that I'll show you how duality, how come it's so very powerful. All right. Let me show you. What if I wanted the transform of this, the inverse Fourier transform of this? Now listen to me. Suppose I said in the frequency domain, my x of omega was equal to a pulse function of width 2b, centered, just of omega, so it's centered at 0. It could be rendered as rect of omega over 2b, right? Now that's in the frequency domain. Drawing that out there, the width of this would be 2b, or this would be minus b here, and this would be b, and the height would be 1, and this would be a pulse function of width 2b of omega, and remember this is omega. Now you look at that, I want to know what caused that. So I want to know what x of t would cause that. And then we're going to say, first, what does that look like? Just look at that property. I have a value of 1 from 0 to b, right? And 0 beyond there. That's the frequency domain. Think of a filter. What filter does that look like? If that's h of omega, not x of omega.
A bandpass filter?
Well, yeah, but it really looks like an exact, perfectly low-pass filter, right? because it's centered at 0, isn't it?
Oh, yeah.
Isn't that right?
Sorry.
Now, if you shifted that up in frequency, then it would be a true bandpass. This is a perfect low-pass filter. It passes everything if this is h of omega, right? I'll even call it, I'll let this be called my h of omega. It is the Fourier transform of the impulse response of the filter now. We're going to assume that. Some of you know where I'm going with this. Are you following me? Y'all know when you have a low-pass filter, ideally you would pass everything up to the point where it's called the stop point or the stop band, right? And then nothing goes past that frequency, right? Now here's something the Fourier analysis shows you where we get into causal and non-causal effects. And I'll show you, this is perfect. So how would you figure that out based on your knowledge of things? If it was in the time domain, could we get it? What if that was instead of as a function of omega, so suppose it was a function of t. Do you know what the transform is? We just did it. It would be what? Tau times the sink of omega tau over 2, right?
Yeah.
Y'all with me? So if you see something, if you see any kind of a functional form, that's a pulse in the frequency domain, and you want the time domain, signal that caused it, then you use reciprocity. Now, what does reciprocity say again? I'm going to go back over here and make sure you see this, because I'm spending time on this because I know how important it is. I mean, if you don't see it, you got to spend time on this to see just how powerful this is. Technically speaking, if this was given as h of omega and you wanted h of t, then the inverse Fourier transform would be this. We don't ever do this, but the inverse Fourier transform, x of omega, would be given as simply 1 over 2 pi times the integral from minus infinity to infinity, or I should say, this would be x of t, pardon me. Or, yeah, I can call it x of t here, or h of t to be honest with you, because this is an impulse we're talking about. H of t would be 1 over 2 pi, the integral of h of omega times e to the j omega t d omega. Now, you could, in fact, put that in here and do this integral. It's not that hard an integral. You can do it. You'd waste too much time doing it that way, but you could do it and get h of t. What you could do, that's true, you could do it this way, but if you use reciprocity, let me show you the power of reciprocity. Reciprocity says if I have x of t, and I know it renders me capital X of omega, we know that transform pair, then if we take the mathematical form of x of omega over to the time domain, replace omega with t, if that's a pulse, this is a pulse. Follow me? Understand? Then, over here, you would take 2 pi, and you would take small, whatever the functional form is there, and replace t with minus omega. This is duality. It's one of the most powerful properties of Fourier transform. It allows you to get transform pairs that are otherwise sometimes almost impossible. Now, when I look at this, what do I see? I really see something that looks like this. I know if I have a pulse function of t, right? I know that renders tau times the sink of omega tau over 2. Correct, class? Right? We know that. So if I have this in now the time domain, this becomes tau times the sink of not omega, but t tau over 2. Then in the frequency domain, now I take that p tau over t times t and put a 2 pi, and then I put p tau, but not t, but minus omega. Are you with me? Now I have a question for you. How many see what I've done? Reciprocity. Make sure you study that and really know it. I test this hard on the exams. You get it. You really are going to be tested on this. So now, when that happens, tell me about this. Can I make that a plus omega and 1? Think about what a pulse function looks like. Where is it centered at?
0.
At where this argument is where 0. This, what you said, minus omega equal to 0, but where omega is 0. Well, is minus omega at 0 the same thing as plus omega? Yes. In fact, that plus, you can replace this by plus. I prefer you do. Are you with me? think about it. Delta of minus omega is the same thing of delta of plus omega, right? Pulse of minus omega is the same as pulse of plus omega because it's what? An even function. That's the real reason. Do you agree with me, class? Now, when I look at that, I'm going to divide by 2 pi to get the scaling, make the scaling problem obvious. So if I divide this by 2 pi, now I can say I have a pulse of width tau in the frequency domain. That's what caused it, right? This is a very important point I'm about to make. It's critical you see this. Now, what's the weight on this one? 1, right? But what's the actual width?
2B.
2b, right? Now I come over here, and I put this as 2b. And that means this is 2b, or really, this is going to be b over pi. I have a comment here. And now you can see that this, b is always the bandwidth, and it's always from 0 to the point the filter cuts off. You never worry about negative frequencies, all right? The bandwidth is always going to be the width from 0 to here for a low frequency filter. But there's something very strange about this. And I'll show you what I mean when we get to quiz. If I have a filter here, and I have h of omega, and a delta t comes into that filter, then my output is the impulse response. This has actually got b over 2, so this is tau b in here too, or tb. What does this function look like? Think about it. If this function doesn't look like this, right here, doesn't it, class? How many see that? That's what this same function looks like. Now, when does this delta function actually come in? At t equals 0, right? But before the delta function comes in, let t equals minus 1 second, there's already output. You all see this? This output's been going on forever. It knew the delta function was going to hit. Do you follow me? Does that bother you at all? If it doesn't, then you don't see what I'm talking about. That's a non-causal response. That's an impossible response. There's nothing in the world that can anticipate the input. Now you can get this stuff, you can have this if you've got a tape recording, a track record of everything, and then you can put a non-causal filter on it. But this filter, like that, never exists in the real-time world. It does exist if you have a strip chart of data, and you can put a data record so we can look forward and backward through that record and find out what's going on. Are you with me? But this doesn't work in real time. Got me? This is an impossibility that gives a non-causal response. So no filter in the real world will ever be that good. Just take that from me. That's the real point I'm getting at. You want your quizzes? I'm trying to make some important points. All right. Here they come back. Do me a favor, at least find us between you and your neighbor, preferably more.